Hello everyone, this is Shiva. I have with me Sushit and Ajay. We are graduate students at Florida Atlantic University. Today we are delighted to give presentation on neural networks in information retrieval. To start with, let's dive into the basics of introduction in information retrieval. Information retrieval or IR is essential the process of finding relevant information from a large pool of data. For example, search engines use IR to find relevant documents based on our queries. The challenge is not only to match words but also understand user intent and deliver meaningful results. To tackle this, we use neural networks, which are computational models inspired by human brains. These networks are built from interconnected nodes or neurons organized in layers that learn from data. By adjusting the connections between neurons, neural networks continuously improve at solving tasks like understanding complex queries. Below are the three main properties that makes them powerful in IR. First, learning from data. Neural networks adjust weights based on errors, making them more accurate over time. Second, they have hierarchical structures. Neurons are arranged in layers with each layer building a previous, enabling the networks to understand complex patterns. Third, neural networks use nonlinear functions. This allows them to model relationships beyond simple linear patterns. So, what makes neural networks particularly useful for IR? First, semantic understanding. Neural networks can grasp the meaning behind words and phrases, making search results more relevant. Handling complex queries. They handle queries with multiple concepts and even ambiguous language, something traditional systems struggle with. The last one, adaptability. Neural networks can adapt to changing search trends, learning from user interactions over time. Now, Sushit will continue.
Thank you, Shiva. Now let's look at some neural network models used in the information retrieval. First, we have the artificial neural networks or the ANNs. So, ANNs are the foundational neural network model consisting of layers of neurons connected by weighted edges. ANNs process information layer by layer, with each layer transforming input data to identify complex patterns. So some of the artificial neural network models includes multi-layer perceptron, a basic form of ANN used in IR. So this is a feed-forward network with input, hidden, and output layers. In IR, the multi-layer perceptrons are used for tasks like document ranking. By training on labeled data, MLPs learn to rank documents based on relevance to a user's query. For example, in the job recommendation system, an NLP can be trained to rank candidates based on keywords matching and relevant scores, helping recruiters finding the best match. The second type of the model is the convolutional neural networks. Though CNNs are widely used for image processing, they are also valuable in text-based information retrieval. They capture local patterns in data, which in text means analyzing sequence of words to understand structure. So by scanning word sequences, CNNs can identify recurring phrases or terms in documents, which improves search relevance by capturing context. For example, in e-commerce, a CNN could enhance product search by analyzing phrases in product descriptions, helping match complex queries like eco-friendly running shoes to relevant products. So why to use ANNs in IR? MLPs and CNNs both improve IR because they learn from data patterns and enable better semantic matching. This is a step beyond simple keyword matching, capturing meaning and context. Next are the RNNs or the recurrent neural network. So unlike feed-forward networks, RNNs are designed to process sequential data, which makes them highly suitable for handling text. RNNs retain information from earlier in the sequence, allowing them to understand word order and context. Since they handle data in sequence, which is important for IR because text is inherently sequential, each word adds meaning based on the ones before it. So, for example, imagine a query asking for most recent advances in career treatment. An RNN processes this phrase word by word, retaining the context and understanding that it's about the recent advances, not just the treatment in isolation. So, the RNNs enable deeper contextual understanding because they don't just read words but also recognize how each word relates to others in a sentence or phrase. This ability to understand complex relationships between words is critical for accurately ranking documents or understanding query intent. The long-term dependencies. RNNs excel in capturing the long-term dependencies, which means they can retain relevant information from earlier in a sentence or paragraph. This is crucial for information retrieval where understanding context can make or break relevance. For example, in a legal document retrieval, queries are often complex. RNNs can handle sentences with many clauses and nuisance, making them better at retrieving precise legal precedents. However, RNNs struggle with very long texts because they tend to forget earlier words as new ones are added. A problem known as the vanishing gradient issue exists. So next are the LSTMs, which stands for long short-term memories networks. They are a type of RNN that address the vanishing gradient problem. It uses memory cells and gates that decide what information to keep or forget, helping retain context over longer text sequences. So coming to the structure of an LSTM, each LSTM unit has three main gates: the forget gate, input gate, and the output gate. The forget gate determines what information from the previous cell state to forget. The input gate decides which new information to add to a cell state, and the output gate selects the information to output based on the updated cell state. So this structure allows LSTMs to selectively remember critical information, which is essential for handling complex context-dependent queries. So coming to how LSTMs improve the information retrieval process is by managing dependencies over long texts. LSTMs are well suited for IR tasks requiring detailed understanding like question answering or information extraction. For example, in medical information retrieval system, a query could ask for research articles on long-term effects of a specific drug. An LSTM can understand that long-term effects and specific drug are the main focus, enabling more precise retrieval. So LSTMs are inspired by the way human brain process information using memory and forgetting mechanisms. So this enables the IR system to retain context and adapt the responses based on recent information, much like human memory. So next are the transformers, which are the latest evolution in neural networks for information retrieval, especially known for their role in advanced language models like BERT. They process data more efficiently than the RNNs because they rely on an attention mechanism rather than the sequential processing. The attention mechanism allows transformers to weigh the importance of each word in a sentence, helping them focus on relevant parts of a query or document. This is especially useful in information retrieval where certain words or phrases in a query carry more weight in finding relevant documents. For example, if a query is best outdoor equipment for winter, the attention mechanism helps the model understand that outdoor equipment and winter are the key focus points. Transformers are unique in their ability because of the parallel processing, uh, which is their ability to process data in parallel, making them faster and more efficient than RNNs. It allows transformers to handle large datasets quickly, which is ideal for large-scale IR applications like web search engines. Now let's review some case studies. First is the Google search with BERT. In 2019, Google integrated BERT, which stands for Bidirectional Encoder Representations from Transformers, into its search algorithm, making one of the most significant improvements in search relevance. Improved Google's understanding of natural language queries, particularly with longer and more conversational queries by grasping context and intent. For example, if previously if someone searched for 2019 Brazil traveler to USA needs a visa, Google might have written results about US citizen traveling to Brazil. But after integrating with BERT, Google now understands that the search intent is about Brazilian citizens needing a US visa. So this case study highlights how transformer-based models enhance query understanding and improve search relevance. The next is the Microsoft's Turing model for Bing search. Microsoft developed a Turing Natural Language Generation (TNLG) model and integrated it into Bing search to improve IR. Turing model significantly improved relevance in Bing by handling complex queries, providing a better contextual understanding. For example, Bing uses Turing models for document ranking and passage ranking, improving the accuracy of search results and user satisfaction. So next is the Amazon's neural search for e-commerce. Amazon employs neural networks in its product research system to enhance the relevance of search results and product recommendations. So using neural embeddings, Amazon improved its search capability. For example, if a user search for outdoor jackets, Amazon neural network model considers user behavior and trends to recommend products. So this case study highlights the application of neural IR in e-commerce, where relevance and personalization directly impact sales and customer satisfaction. Now Ajay will continue.
Thank you, Sushit. So, moving on to embeddings and semantic representation. Embeddings are a core concept in neural information retrieval. To improve how IR systems match queries with relevant content, we use embeddings to represent words, sentences, or even entire documents as dense vectors. This means that each item is mapped into a multidimensional space where similar items are closer together. For example, word embeddings allow IR system to capture the understand relationships between words. For example, words like king and queen are mapped closely together because they share similar contextual meaning, while king and car could be far apart. This spatial arrangement enables the model to recognize relationships such as synonyms or even analogies like king is to queen as man is to woman. Role of sentence and document embeddings is such that it is an extension of this idea. Instead of focusing on individual words, these embeddings capture the overall meaning of a sentence or document. So if a user's query is where can I find the pizza in New York? The model prioritizes documents that mention pizza places in New York, even if the wording differs from the query. This is because the embeddings encode the following semantic context and not just specific keywords. The semantic representation helps in delivering more relevant search results and enables IR systems to better understand intent, making search results feel more accurate and intuitive. Embeddings have been game changer for search engines, allowing them to match intent with content effectively. Moving on to the applications of neural networks in IR. So one of the main applications is document ranking. First application is uh, neural networks help rank documents by analyzing how well each document aligns with a user's query. Unlike traditional ranking methods that rely on keyword matching, neural models can access the relevance of documents based on deeper semantic features, which ultimately leads to a more personalized search experience. For example, if you search for best family friendly hotels in Paris, a neural IR system can prioritize results based on reviews that emphasize family friendly amenities, even if those specific words aren't repeated verbatim in the query. Next application would be query understanding. Another powerful application. Neural models are excellent at interpreting user intent by considering the context of each query. These models recognize synonyms, rephrased questions, and even domain specific jargon, which is essential for specialized fields like medicine or law. For example, if someone searches for heart attack, the model knows to include content about myocardial infarction as well as as well, enhancing the user experience by broadening the scope without compromising relevance. Next application would be information extraction. Neural networks also excel at information extraction, which involves pulling out specific details from text. Imagine if you are looking for all instances of a particular person or date across a document database. A neural system can identify and extract these entities without requiring manual filtering. And the last but not the least application would be recommendation system. Finally, neural networks underpin recommendation system which suggest content based on users' previous behavior and preferences. This could be in form of articles, products, or videos. Recommendation systems continuously learn from interactions, adapting to users' tastes over time, which is crucial for platforms that thrive on engagement, such as Netflix. Now, addressing the challenges and limitations. Despite these advancements, neural networks face severe challenges that are critical to address for broader, more reliable application in IR. The first challenge is interpretability. Neural networks are often seen as black boxes which because it's difficult to understand how they arrive at certain results. This opacity makes it challenging to trust their recommendation in fields where accountability and transparency are crucial. For example, in healthcare applications, users want to know why a certain document or recommendation was prioritized over others. Without a clear explanation, it's hard to validate the system's decision making process. Another limitation would be high data requirements. Neural networks generally need large volumes of labeled data to train effectively. This can be an obstacle, especially for smaller organizations that may not have the access to vast datasets. If a small business wants to build an IR system, obtain enough data to train a high performing model can be costly and time consuming, making it difficult for them to compete with larger companies that have extensive data resources. Finally, computational complexity is a significant barrier. Training and deployment of neural models require substantial computing resource, which are not always feasible for every organization. High performance GPU or TPUs, for example, are often necessary and associated cost can be prohibitive. So finally, moving on to conclusion and future enhancement, neural networks can have made significant contributions to IR, enabling more sophisticated and accurate research results. Future research directions include developing more interpretable and efficient models, addressing data scarcity, and exploring novel data architectures. Thank you.